Welcome to Inorganic Chemistry. Today, we are going to unlock one of the most powerful tools for understanding how atoms behave, Slater's rules. We will learn exactly how electrons interact with the nucleus and with each other. Let us start by imagining you are at a crowded rock concert. The lead singer on stage is the positively charged nucleus, and the fans are the negatively charged electrons. If you are in the front row, you feel the full energy of the performance. But if you are in the back, the fans in front block your view. In an atom, inner electrons block or shield the outer electrons from the full attractive force of the nucleus. This is called the shielding effect, and it is crucial for understanding atomic behavior. Now that we understand what shielding is, let us look at how we measure it mathematically. The actual pull an outer electron feels is called the effective nuclear charge, or ZEF. It is calculated by taking the actual atomic number, Z, which is the total number of protons, and subtracting S, the shielding constant. The shielding constant represents the total blocking effect of all other electrons. If S increases, the effective pull decreases, meaning the electron is held less tightly by the nucleus. Before we calculate anything, let us see this with a concrete visual. Here we have a diagram of an atom. In the center is the positively charged nucleus, labeled Z. Surrounding it are rings of blue inner electrons. Notice the dashed arrows pointing outward. These represent the inner electrons repelling and shielding the outermost red electron. The solid black arrow shows the net attractive force reaching that outer electron, which is ZF. This visual perfectly captures our formula, the total nuclear charge minus the shielding effect. This formula we just saw leads us to an important question. How do we actually find the value of S? In 1930, physicist John C. Slater proposed a set of rules to calculate this. The first step is to write out the electron configuration and group the orbitals in a very specific order. We group 1s alone, then 2s and 2p together, 3s and 3p together, 3d alone, and so on. Once grouped, we completely ignore any electrons to the right of our target electron, because outer electrons do not shield inner ones. Now that we have our groups, let us assign the shielding values. If our target electron is in an s or p orbital, we follow these specific values. Every other electron in that exact same group contributes 0.35 to the shielding constant. Electrons in the next shell down, the n-1 shell, are closer to the nucleus and shield better, contributing 0.85 each. Finally, all electrons in even deeper shells, n-2 or lower, are excellent shielders and contribute a full 1.00. The rules change slightly but significantly if our target electron is in a d or f orbital. Just like before, any other electron in that exact same group contributes 0.35. However, because d and f orbitals have complex, diffused shapes that do not penetrate well toward the nucleus, all inner electrons shield them perfectly. Therefore, every single electron in any group to the left contributes a full 1.00. This distinction is vital for understanding transition metals. Now that we have our rules, let us apply them to a real atom. We will calculate the effective nuclear charge for an outermost 4s electron in zinc, which has an atomic number of 30. First, we write the grouped electron configuration. Our target is one of the 2 electrons in the 4s group. This means the other 4s electron is in the same group. The third shell is our n-1 shell, containing 18 electrons. The first and second shells make up our n-2 groups, containing 10 electrons. Continuing with our calculation, we now multiply our electron counts by their shielding values. We have 1 electron in the same group, so we multiply 1 by 0.35. We have 18 electrons in the n-1 shell, so we multiply 18 by 0.85. Finally, we have 10 electrons in the n-2 shells multiplying 10 by 1.00. Adding these products together gives us 0.35 plus 15.3 plus 10.0, resulting in a total shielding constant of 25.65. With our shielding constant calculated, we can now find the effective nuclear charge. We take zinc's actual atomic number, 30, and subtract our shielding constant of 25.65. This gives us a final effective nuclear charge of plus 4.35. Physically, this means that even though there are 30 protons pulling on it, the inner electrons block so much force that the outermost electron only feels a pull equivalent to about 4 protons. This explains why zinc easily loses these 2 electrons. Let us compare that result by looking at a different electron in the exact same zinc atom. This time, our target is one of the inner 3D electrons. According to Slater's rules, we must completely ignore the 2 electrons in the 4s group because they are to the right of our target and provide no shielding. For the remaining electrons, we have 9 other electrons in the same 3D group and 18 electrons in all the groups to the left of the 3D orbital. Continuing with our 3D electron, we apply the special rule for d orbitals. The 9 other electrons in the same group each contribute 0.35. Because our target is a d electron, every single one of the 18 inner electrons to the left contributes a perfect 1.00 to the shielding. Multiplying these out, we get 3.15 plus 18.00. This results in a total shielding constant of 21.15. Finally, we subtract this new shielding constant from the atomic number 30. 30 minus 21.15 gives an effective nuclear charge of plus 8.85. Notice that this is significantly higher than the plus 4.35 we calculated for the 4s electron. The nucleus pulls on the 3D electrons more than twice as strongly as it pulls on the 4s electrons. This perfectly explains why transition metals like zinc lose their outer s electrons before their inner d electrons. To wrap up, Slater's rules provide a highly effective, systematic method for quantifying the shielding effect in multi-electron atoms. By simply grouping orbitals and assigning specific values, we can calculate the effective nuclear charge any electron experiences. This simple mathematical tool bridges the gap between abstract quantum mechanics and observable chemical behaviors. Mastering these rules allows you to confidently predict periodic trends, ionization energies, and the chemical reactivity of elements across the entire periodic table.